Hi, this is Stephen Breyer from Art Valley Community College. This is for CSIT 256 Computer Architecture and Assembly Language. And this is the overview for Stallings Chapter 4. By the way, there's going to be another video that's going to go over, I'll just jump ahead to cache mapping algorithms. And there's a example in a PDF that's up in Canvas. And this other video is going to go over that in a little more detail. So chapter 4, one of the first things it shows is this pyramid, and the idea, this is the memory pyramid, memory hierarchy. And if you glance at the slides, you'll see that on top would be like registers, and then there's cache, and then there's memory, and it goes down from there, and then magnetic tape is at the very bottom. And the idea in the hierarchy, closer to the top, the memory is more expensive, but it's faster. Closer to the bottom, memory is cheaper and slower. And also in terms of cost, usually the higher end of the hierarchy would be, cost more per bit than the lower end. And so that's just one of the things that's covered. And so from a computer manufacturer point of view, they're kind of like balancing, trying to get to a certain price point, how much memory the computer has, how much cache the computer has, and then when doing the processor, how many registers that the CPU has, and so it's sort of a balancing act that the computer manufacturers will go through. But the focus on this chapter is going to be cache. Now, let me jump ahead to next week. Oh, it's not next week. Well, yeah, it is next. Well, I'm losing track. I'm so confused. In Stallings Chapter 5, we'll take a closer look at dynamic memory versus static memory. And static memory, now both of them are volatile, so if we lose power, they both forget what they have. So they both need power in order to retain their data. It's the dynamic memory, the DRAM, which we use for primary memory, it degrades, and so it has to be refreshed. Static RAM does not have to be refreshed. Dynamic memory, when you read it, it's destroyed, and the memory module actually has to write the data back. Static RAM, when you read it, it's not destroyed. It uses flip-flops in order to get the data back. So since it's too expensive to make all of primary memory static RAM, then that's where the static RAM is used for cache, which is a portion of memory. And so the idea behind it is that when the CPU is looking for memory, it's going to peek at the cache first to see, is it there? Because if it's there, it's faster memory, it's closer to the CPU, it's quicker and faster to get it from there. If it finds it, great, that's called a hit. If it doesn't find it, that's a miss. And then what will have to happen is that the memory will have to be taken, or the data will have to be taken from memory onto the cache. When it does a block at a time. And the idea of doing a block at a time is that if the CPU needs the next byte, it's already there in terms of that block. So the idea is that for subsequent reads to the same block of memory, they'll go faster if they're already in the cache. So data going from the cache to the CPU is a word, and data going from memory to cache is a block. The blocks are larger, the words are smaller, and what the CPU is doing is just glancing at the cache to see, is the word it's looking for there, and if it is, great, and if not, it'll have to go to memory in order to get it. The idea is that a block from memory will reside in a line in the cache. So when computer manufacturers or the processor manufacturers are making the cache, one of the things they will determine is how big the line should be, how big should the block be that's brought into the cache, how big should the cache be. Now, no joke on this, there's some people that get their doctorate on analyzing what the best size cache is for the best kind of applications that are running. Because what'll happen is some applications will lend themselves to needing larger caches than other. I'm over-exaggerating. It's a bit simplistic than that, but what I'm getting at is it's a complicated thing, figuring out the size of the cache, the number of caches, and then within the size of the cache, the size of the line, etc. So as I mentioned at the very beginning, that there'll be another video that's going to go through the cache mapping, and the idea in the cache mapping, where does the CPU look in the cache? So in direct mapping, it looks at a specific line. In associative mapping, it looks at all the lines. In set associative mapping, it'll look at a set, and then it'll look at all the lines that are in the set. They each have advantages and disadvantages of each. What that other video is not going to get into, it makes a reference to it, but block replacement algorithms. So the idea is, so let's say the CPU is looking, we'll take this one for example. Let's say in direct mapping, the CPU looks in a particular line to see if the block is there. If the block isn't there, then there's no choice. That one has to be removed, and the next block comes in. If you're talking associative, where a block can reside on any line, well, suppose all our lines are full. Let's say the CPU scans the cache, looks at all the lines in the cache, doesn't find the block it's looking for, so it has to bring the block in from memory. But the cache is full. So one of the blocks that's currently in the cache has to be removed. So the block replacement algorithms will identify, well, which one is removed. Is it just the oldest one there, so first in, first out? Is it the least recently used? When has it been used in a while? Because there could have been something that's been in the cache for a while but keeps being referred to. Or is there the least frequently used? So let's say there was a block that was only referenced one time and everything else is referenced a lot. Then we'll pull that out. And the last thing the chapter will look at is the write policy. And what we mean is that the CPU is writing data back to memory. Does it just leave the change in the cache? And so now the memory and the cache are not in sync? Or does that write have to go back to memory? And since memory is slower, then the writes, there's a hit in terms of performance as it writes it back. That was a long overview. I'll rethink that.